Hello, class. This recorded lecture for, again, section 8.1, which is linear system analysis, basically, but solving linear equations. We started with two equations, two variables, with two unknowns, with two equations, and we're moving up to three equations. And again, remember, these are all linear. And when we move up to three equations, we're going to have three unknowns. So we have x variable, y variable, and now we're going to add the z variable. And again, the idea is that we want to provide you with a process that to solve these, very similar to the way that a computer would be programmed to solve these. And so this is called, again, the elimination technique. And let me just walk you through a couple things here on the slides before we get to an example. So when you have a three-dimensional figure that's linear, instead of having just a flat surface now, we have volume. So what we're doing here now is with the third dimension, instead of just having a flat surface with a line, with all three, we have a plane. So we have the x, y, and now the z will give us some height. And the idea is that everything's linear, so we're not going to have spheres or cones or anything crazy like that, but all these would be planes. And the one that we're going to be focusing on is A. And this is the idea, is that you have a consistent solution, but there's only one solution. So these three planes will meet at one single point. You could also have consistent solutions where they could meet with regards to a line solution where one variable could be a line and the other two are unique. And we're not going to really focus on that. And then the last one is when none of them actually intersect at some place. You could have three parallel planes, which is pretty easy to explain, but you could also have them kind of just intersect in two out of three variables. And so for those of you heading on to some higher level maths, you'll talk about that in that class. So what we're going to focus on actually is the first one here, and just try to be able to solve three equations, three unknowns for a single solution. And this idea that we are going to be using is called the Gaussian elimination. So it basically is elimination, just like we talked about with two equations and two unknowns, except now, I guess mathematician Gauss is the first one to come up with this technique, so I guess it's named after him. But the strategy is like this, is that you want to solve, we'll have three equations, and what you do is you want to solve one of the equations, one variable equals something, the next equation will be two variables equals something, and the third one will be three variables equals something. And the strategy is, once you have that, you'll solve for the first variable and do this idea of substitution of those variables to solve for the second equation, and then the third equation. I think the mathematical term is called back substitution, but that's okay. The terms aren't that important. Just to refresh your memory, if you didn't watch the first slide, the first video recording, here are the operations that you could do for elimination. You can change two equations. You can multiply both sides of one of the equations by a non-zero number. And the third thing is you could add two equations and replace that new equation, the addition of those new equations, and you could replace one of the equations. So that's how we eliminate variables. So the strategy, just like we did in two variables, the same with three, except just a little more tedious. So let me see if I could get this going here on the whiteboard and walk through an example for you. Okay, so I paused it there to write up these equations that we're going to solve up here on our whiteboard. And so here's our three equations, and I've labeled them equation 1, equation 2, equation 3. So the strategy is to take the first equation and use that to eliminate one of the variables in the bottom two. And so I'm just going to pick the X. One of the reasons, that's what I have in my notes, but you could pick the Y or the Z too. And sometimes it depends on how the equations are configured, which one might be the best one to do. So you could rearrange the equations if you want. That's one of the three things that you could do in the elimination technique. But the equations that we have and the way they're ordered is just fine. So the strategy is to use the top equation to get rid of the X variables in the bottom two. So let's start by taking equation 1 and multiplying it by -1. So what that'll do is change the X to minus X. So if we add it to equation 2, guess what happens? The X's cancel out. So that would be our strategy. So we'll have minus X minus 3Y, right? Minus 2Z equals minus 9. And so then we just take equation 2 here, plus 3Z equals 16. And let's add these two equations up. So this would give us 0x, and then this would be minus 4y, minus 2 and plus 3 is plus 1, so that'd be plus z. And 16 minus 9 would give us 7. So this is going to be, and let me put it in red now, this is going to be our new equation 2. So what's the next strategy? Well, the next strategy now is to get rid of the X value and, or the X variable, excuse me, in equation 3, again, to use in equation 1. So what do we want to do in this case? Well, in this case, let's do this one in green. We multiply equation 1 by the number -3, right? You would see we'd have minus 3 and plus 3x, and so those would cancel. And again, that's our strategy. So we'd have minus 3x, and then 3 times 3, we have minus 9y, minus 6z, and 9 times minus 3 is minus 27. So we bring down equation 3. So let me just label this. This was equation 2. So this is equation 3. So it'd be 3x minus 4y plus 2z equals 28. So again, we'll do our addition. These two cancel. And so we'd get minus 13y, and then minus 6 plus 2 is minus 4z, and minus 27 plus 28 would give us 1. So when we reorient this, let me do this in red. Our new equation 2 is minus 4y plus z equals 7. And our new equation 3 now is minus 13y minus 4z equals 1. And so now what we want to do is to use the new equations 2 and 3 and eliminate one more variable. So we could replace that. So looking at these two equations, it's easier to get rid of the z variable than it is the y. And if you're a computer, you don't care. You can multiply and divide by any number and it doesn't bother you. But the smaller numbers are usually better, right? Or here we have 13, kind of a big number, and 4. So we're going to be bigger numbers if we try to eliminate the y. So what I'm going to do is try to eliminate the z. So what I'm going to do here, and again, I'll do this in green, is I'm going to take the new equation 2 and multiply it by 4. So what was that going to do for me? It'll give me 4z here, and 4z and minus 4z will cancel out. So minus 4 and 4 is 16. So we have minus 16y plus 4z equals 28. 4 times 7 is 28. And now we have, this is equation 3. We just bring it over and we'll do the addition again as well. So if we do that, the z's will cancel, and that was our strategy. And so 1 and 28 is 29. And it looks like we have minus 29y equals. So we could use new equation 3 here. And I'll put it in green. Minus 29y equals 29. Okay, so now we've set it up where we have one equation with one unknown, one equation with two unknown, and one equation with three unknown. So let me put here in boxes the three equations that we have left. We never changed the first one, so we're using that. This is the second equation, right? And then we replace that one, so here's our third one. So what we want to do now is solve for the three variables. So you start with equation 3, and we do minus 29y equals 29, divide each side by minus 29. You see it's nicely set up where y equals minus 1. So now we'll take equation 2 and plug minus 1 in for y and solve for z. So we have minus 4 times minus 1 for y plus z equals 7. So that would be what? 4 plus z equals 7. Bring the 4 to the other side, and z would equal 3. So now we go back to equation 1 and solve for x. So we have x, and then we have plus 3, and then y is minus 1. So we plug minus 1 in, and then plus 2, and z is 3 equals 9. So it'd be x minus 3 plus 6 equals 9. And so if you simplify this, this would be x plus 3 equals 9. So solving for x equals 6. 9 minus 3 is 6, not 3. So here's our three solutions. Sometimes you end up putting it in ordered pairs, and the ordered pairs would look like this. Usually it'd be x first, y second, and z third. So if you did that, it would be 6 minus 1 and 3. So this is a step-by-step example, again, going over this idea of elimination. And you know what? I think I'm going to do one more example. So I'm going to pause, erase the board, and get another example up here. So here's the second example I'm going to walk through. Again, three equations, three unknowns, and walk through the elimination technique again. I'm going to leave the equations in this order. The first one is the simplest, and that's usually the one you want to put on the top anyways, or the one you want to use. And so looking at these numbers, let's just get rid of the x variable first. So again, strategy is use the top equation to get rid of the x variables in the next two. So what are we going to do? We'll multiply, let's do this in blue, equation 1 by, say, minus 4. And so that would give us minus 4x minus 4y plus 4z equals 4. And if we bring over equation 2, and just bring it over, it would be 4x minus 3y plus 2z equals 16. So if we add these together, the x's cancel. That was our strategy. And we have minus 7y plus 6z equals 4 and 16 is 20. So that's going to be our new equation 2. So let's do the same thing, except now we want to get rid of the 2x in equation 3. So we'll take equation 1 and multiply it by minus 2. And that will give us minus 2x minus 2y plus 2z equals 2. And we have 2x minus 2y minus 3z equals 5 from equation 3. So let's add these together. Again, the x's cancel. And 2 minus 2 is minus 4. And then we'd have minus z. It looks like that would equal 7. So our new equation 2 is minus 7y plus 6z equals 20. And our new equation 3 is minus 4y minus z equals 7. So if you take a look at that and you say, all right, what would be the next variable that I want to get rid of using the two new equations with two variables now? And so it looks like the z variable would be a little bit easier to get rid of than the y variable, just because you could see in equation 3, you just have minus z there. So if you wanted to get rid of z and say, the top equation, that when you add them together, you would just multiply equation 3 by the number 6. So let's do that in green. So you're going to take equation 3 and multiply it by the number 6, and it would be minus 24y minus 6z equals 42. And then you would bring over equation 2. That would be minus 7z, or y, plus 6z equals 20. So again, when you add those two together, the z's cancel. And so what do we have over here? We have minus 31y, and this would equal 62. So let's make that our new equation 3. Minus 31y equals 62. So now we have the three equations. Here is the one with the single variable. We'll use this one for the two variables, and we'll use the top one for the three variables. So again, this is called the back substitution technique, I believe, but you start by solving for the first variable. And let's see here. Let's do that in brown, see what that looks like. So if we go to equation 3, we get minus 31y equals 62. Divide each side by minus 31, and you get y equals minus 2. So now you take equation 2 and plug in the y value. So it'd be minus 7 times minus 2 plus 6z equals 20. So this would be 14 plus 6z equals 20. 6z equals 14 minus 20 is 6. See how it's nicely set up. So z would equal 1. Okay, now we use the top equation to find the x value. So it'd be x minus 2 minus 1 equals minus 1. So when we set this up, this would be x minus 3 equals minus 1. And you bring the minus 3 to the other side, and x would equal 2. So again, if you put that in the ordered pairs, it would be x is 2, y is minus 2, and z is 1. So those are two examples, two good ones actually, to kind of walk through the elimination technique now using three variables. I tried to set up the homework in my math lab so you could get integer numbers for your solution. I hope they don't change it on me, but the ones that I chose for you to do are going to be very similar to what we just did here in the recorded lectures. So that ends the recorded lectures for section 8.1, solving a system of linear equations.